for you that deals with combinatorics, fancy word for counting. It's a topic normally covered in a discrete math course. We use things like permutations, combinations, combinations without replacements, various other counting, generating functions. But this is the mathematics of counting, and this is a fairly rudimentary question. It says, for how many integers n is this expression, this quotient that depends on n, an integer? Now, just to be sure, folks, 11 over 3 is not an integer, right? 11 divided by 3 does not reduce. It's a mixed fraction. It's equal to 3 2/3, right? 12 over 3 actually reduces to an integer, and that's what we're talking about here. 12 over 3 is equal to 4. That's a natural number, a positive integer. Okay. So again, we want to look for a scheme to help us count the number of times you can evaluate this expression at an integer and get an integer in return. Okay, now, y'all, this next step, I didn't show you the steps of the long division. I don't think you'd have enjoyed that so much. But after a long division here, we get this statement right here. Okay. Again, this is not hard to do. You can do something called synthetic division also if you opt for that for when you're dealing with linear factors. Put a little -5 out of there and put a 1, 1, 0, 6, 7. Do some work and you would determine whether or not, you would determine whether or not n+5 was a factor, and you'd also determine, more importantly in this problem, this remainder 477. Now notice for this entire thing, this entire part right here, this entire part, the cubic part of this is definitely an integer just by closure, right? If you evaluate this cubic equation at any integer value just by closure, an integer cubed is an integer back and so on, right? So this entire piece is an integer already, right? So we don't have to worry about this part out here is called the dividend, I think, but anyway, not important. But this object right here is an integer just by the closure of the arithmetic of the integers. Now notice right here we need for n+5. n+5 must be a divisor, okay? A divisor of 477, excuse me. Of 477. And that's very clear, right? Whatever the divisors are of 477, n+5 must be one of them in order for this part to be an integer, right? So that makes sense. So it makes sense to also look at the prime factorization here. This is not hard to do, folks. Notice that there's a rule for division by 3. D would divide the sum of the digits here. 3, I should say 3. Right here, 3 would divide, and y'all, I'm going to use this vertical bar. It would divide the sum of the digits 4 plus 7 plus 7. 4 plus 7 plus 7 is 18, right? And 3 divides 18, of course. All right, so we get this. And that's why you would shop around for 3. And it turns out 3 is a divisor twice. Now, another way to write this, it gives you kind of a heads up on how many divisors you're going to have. You can write this as 3 squared times 53 to the first power. All right, now you may think that exponent of 1 is superfluous, but that gives you, there's a known combinatorics result that says the number of divisors would be 3 times 2 equals 6. Okay. Now again, this step's not absolutely necessary. You're pretty convinced that these are all 6 of the divisors down here based on the prime factorization, right? We have 1, 2, 3, 4, 5, 6 divisors, right? And they're easy to compute based on the prime factorization. But this is kind of a terminate condition. 2 plus 1, this 2 plus 1 gives you 3, and 1 plus 1 gives you 2. You have to account for 0 being an exponent is why this little trick works, okay? So these are some of the divisors. Now notice that there are 12 divisors because a negative number is a divisor, 12 divided by -3 is -4. 12 divided by 3 is 4, right? So there's actually 12 divisors here. And that's actually the answer to our question, because all you have to do is set n+5 equal to all those divisors, right? And solve for n. There's 12 divisors, which is a tantamount to being the same, it being the answer to the question, because you would have to solve this equation 12 times, equals to n+5. right? Okay, that's kind of cool. So without lifting more than a little finger here, the answer to the question is 12. Okay, the answer to the question is 12. Now let's just do a concrete example. Notice that 9 is a divisor in our list, right? So we said n+5 equals to 9. That implies n is equal to 4. This is our original expression. So when you raise 4 to the 4th power, you get 256. When you cube 4, you get 264. And anyway, here's all the arithmetic for you folks. Again, this is divisible. This one's divisible by 9 by testing, and also just by doing it right. 9 times 39 is equal to 351, right? So we got something that is an integer just for 9, and you could check this out for all the larger numbers. Would be a much more painful process. Like for example, 477 would lead to what? I mean, if you put 477 right here, you would have to do 474. Not much fun plugging that in there. But based on the analysis, it would produce an integer, a ginormous integer also. But again, this is the solution. 12 is the solution. Just one last comment. If this divisor were, say, a quadratic, you wouldn't have this one-to-one business going on. You see, you can equate n+5 linearly, to this. You're always going to have a solution. You wouldn't necessarily have an integer solution if you had a quadratic expression in here, right? You'd have to check each one, right? So the linear factor makes the problem, I won't call it trivial, but pretty straightforward. Okay, but in any event, the answer is 12. Thanks for watching.